Welcome to the second of our differentiation lectures. In the first lecture, we looked at what differentiation was and why it was important. In this lecture, we look at various rules that need to be applied to functions so that we can differentiate all of them. There are two types of rules that can be applied to the differentiation of functions. There are specific rules, such as the differential of x to the n and the differential of 1 over x, which we saw in the previous lecture. There are also more general rules, such as the differential of the sum of two functions, u plus v, and the differential of the product of two functions, u times v. These can all be derived from our basic definition of a differential as the limit, as delta x tends to 0, of the change in f over the change in x. Now written out in full, this is f of x plus delta x minus f of x all over delta x. The first rule we'll have a look at is the sum rule. Here we let u and v be functions of x so that f of x is equal to u of x plus v of x. That's a bit cumbersome, so our shorthand notation for that is f is equal to u plus v. That still means f of x is equal to u of x plus v of x. Again, as a shorthand notation, we can have the differential of u of x plus v of x as u plus v as a differential of x. And that is equal to the limit as delta x tends to 0 of u plus v of x plus delta x minus u plus v of x. In other words, just the difference in the f values. And that's all over delta x. Now if we expand that out, we get the differential is equal to u of x plus delta x plus v of x plus delta x minus u of x minus v of x, again all over delta x. Now with a little bit of rearranging, what we end up with is the differential as being the limit as delta x tends to 0 of u of x plus delta x minus u of x over delta x plus v of x plus delta x minus v of x, again over delta x. Now that's just two definitions of the differential of each of the functions u and v. So we can write that as the differential of u plus v of x is equal to u, the differential rather, of u of x plus the differential of v of x. As an example, we'll take that f of x is equal to sine x plus x squared. Now sine x, the differential of sine x, is cos x, and the differential of x squared is 2x. So the differential of their sum, sine x plus x squared, will be f dash of x is equal to cos x plus 2x. Now we'll have a look at a specific rule, the powers rule. Starting from the definition of a differential, f dash of x is equal to the limit as delta x tends to 0 of delta f over delta x. More specifically, we can let, in this particular example, let f of x is equal to x to the power of n, where n is any integer 1, 2, 3, 4 and so on. We need to find the differential of x to the n, or an alternative way of writing that will be f dash of x to the n. Substituting in the equation above, delta f over delta x, our difference quotient, is equal to x plus delta x all to the power of n minus x to the n over delta x. Now x plus delta x to the n can be written out as follows. X plus delta x to the n is equal to x plus delta x, all multiplied by x plus delta x, all multiplied by x plus delta x, as many times as we have. In order to see how x plus delta x to the n expands when raised to a power n, let's look at the first few terms. X plus delta x squared is equal to x squared plus 2x delta x plus delta x squared. We go on to the next power, x plus delta x cubed is equal to x to the power 3 plus 3x squared delta x plus 3x delta x squared plus delta x to the power 3. Similarly, x plus delta x to the power 4 is equal to x to the power 4 plus 4x cubed delta x plus 6x squared delta x squared plus 4x delta x cubed plus delta x to the power 4. We can see a pattern emerging here. What we have every time, in the general sense, x plus delta x to the n is equal to x to the n plus nx to the power of n minus 1 times delta x plus some other terms. Now this notation for O delta x squared means all the terms that have got a delta x squared, delta x cubed, and so on and so forth up to delta x to the power n. Now if we write that out in full, as our difference quotient, we had delta f divided by x is equal to x plus delta x to the power n minus x to the power n all over delta x. Substituting in the equation above, we have this is going to be equal to x to the n plus n times x to the n minus 1 delta x plus all the other terms minus x to the n over delta x. The differential we obtained in the previous slide, delta f over delta x is equal to the complicated expression on the right hand side, can be simplified because we have an x to the power n minus an x to the power n. Those two terms cancel, leaving us with delta f over delta x is equal to the nx to the power n minus 1 times delta x plus some others divided by delta x. Now if we take the limit as delta x tends to 0 of delta f over delta x, the other terms, o to the delta x squared divided by delta x tends to 0, leaving us with n to the x, rather nx to the power of n minus 1, which can be written out more formally as d by dx of x to the n is equal to nx to the power n minus 1, or alternatively, f dash of x to the n is equal to nx to the power n minus 1. Now as an example, d by dx of x to the power 6 can be differentiated to give us 6 times x to the power 5. Similarly, d by dx of 3x to the power 4 is equal to 12x cubed. More complicated expressions can also be derived in this way, so the differential of 4x to the power plus x squared is equal to 12x squared plus 2x. Pause the recording here and have a go at these exercises. Restart the recording when you're ready to continue. Here are the answers to the first exercise. You might want to check your answers before continuing. We can now look at a more general rule, the product rule. Here we let u and v be functions of x as we did before, and here such that f of x is equal to u of x times v of x. A shorthand notation for this, eliminating the x's, is f is equal to uv. Then the rule states that the definition of the differential f dash is equal to uv dash, which is equal to the differential of the first term multiplied by v plus u times the differential of the v term. This is probably best explained using an example. If we take the example, the differential of 3x squared cos x, now that's really equal to 3x squared multiplied by cos x. Now writing this out in full, using the rule, it will be the differential of the 3x squared term times cos x, as cos x is the v term, plus 3x squared, our u term, multiplied by the differential of the v term, cos x. Now if we take the differential of the two bits there, we end up with 6x multiplied by cos x plus 3x squared times minus sin x. Now it gives us the final result of 6x cos x minus 3x squared sin x. Although we defined and used the product rule in the previous slide, we didn't actually prove it, so let's do that now. As before, f of x is equal to u of x multiplied by v of x, our two functions u and v. More simply, this can be written in the x's as f is equal to uv. This means that f of x plus delta x is equal to a term u of x plus delta x multiplied by v of x plus delta x. Now, our x plus delta x applied to our function u will give us a u plus delta u term and a v plus delta v term as a result. So we can rewrite this as f of x plus delta x is equal to the product of two terms, u plus delta v multiplied by v plus delta v. So that the change in uv, delta uv, is equal to u plus delta u multiplied by v plus delta v minus the term we started with, uv. Expanding the brackets, we end up with delta uv is equal to uv plus delta uv plus delta vu plus delta u times delta v minus uv. Now this simplifies to become delta uv plus delta vu plus delta u delta v. The differential then is the limit of delta uv, our difference, divided by delta x. Now this works out to be delta u over delta x times v plus u times delta v over delta x plus this extra term delta u delta v divided by delta x. In the limit, as delta x tends to 0, then delta u and delta v will also tend to 0, leaving us with the first two terms only. Now delta u over delta x is the definition, as delta x tends to 0, is the definition of the differential of u, and delta v over delta x is the definition of the differential of v. Now this leaves us with our result that we've used before. The differential of u times v is equal to the differential of the first term, u, times v, plus u times the differential of the second term, v. Here are some more exercises for you to try. When you're ready, restart the recording. Here are the answers to the second exercise. When you're ready, please continue with the recording. We can now move on to the quotient rule. As before, we let u and v be functions of x, and in this case, so that f of x is equal to u of x divided by v of x. Our shorthand way of defining this is f is equal to u over v. Then the quotient rule states that the differential of u over v is equal to u dash v minus u v dash all over the second term v squared. We can derive the quotient rule in a similar way as we did with the product rule a little earlier. Here we can define delta u over v is equal to u plus delta u over v plus delta v minus u over v. This is simply the difference of two fractions. So applying our normal rules for dealing with fractions, we'll put everything over a common denominator and we end up with delta u over v is equal to v multiplied by u plus delta u minus u times v plus delta v over the common factor of v multiplied by v plus delta v. Multiplying out the brackets, we then end up with uv plus delta uv minus uv minus delta vu over v times v plus delta v. This can be simplified to give us delta uv minus delta vu over v times v plus delta v. We now have an expression for delta u over v as delta u times v minus delta v times u divided by v times v plus delta v. This expression is just the top line of our difference quotient delta f over delta x. So the formal definition of the differential of u over v will be the limit as delta x tends to 0 of 1 over delta x multiplied by our term for delta u over v. In other words, we end up with the limit as delta x tends to 0 of 1 over delta x multiplied by delta uv minus delta vu divided by v multiplied by v plus delta v. An alternative way of writing this will be to write it as follows, as the limit as delta x tends to 0 of 1 over v times v plus delta v multiplied by delta u over delta x times v minus delta v over delta x times u. Note that the delta u over the delta x term is just the definition of the differential of u, and the delta v over delta x term is just the differential of v, so that we end up with the limit as delta x tends to 0 of the differential of u times v minus the differential of v times u over v multiplied by v plus delta v. As delta x tends to 0, this means that we end up with the final expression, the differential of u over v is equal to u dash v minus u dash divided by v squared. Let's now look at an example to see how the quotient rule can be applied in practice. We'll take a fairly straightforward example. Let us find the differential of 1 over x to the power n. Here we let u equal the constant function 1 and v equal x to the n, something we've seen earlier. From the quotient rule, the differential of u over v is going to be equal to u dash v minus uv dash divided by v squared. With u as 1 and v as x to the n, plugging these numbers in or values in, we end up with u over v dash is equal to 0, the differential of 1, times x to the n, minus 1 times the differential of v, which is n x to the power of n minus 1, all over v squared, which is xn squared, which gives us x to the 2n. This can be simplified by taking out the first term to give us minus nx to the power of n minus 1 over x to the 2n. X to the 2n can be written as x to the minus 2n if we bring it to the numerator to give us minus nx to the n minus 1 multiplied by x to the minus 2n. Applying the rules for indices which we discovered in earlier modules, we then end up with minus nx to the n minus 1 minus 2n, which simplifies to become equal to minus nx to the minus 1n minus 1. So our differential of 1 over x to the n is equal to minus nx to the power of minus n minus 1. This can be written alternatively as minus n over or multiplied by 1 over x to the n plus 1. Here are some more exercises for you to try. Pause the recording here and restart when you are ready to continue. Here are the answers to the third exercise. Check your answers, and when you are ready to continue, please restart the recording. Finally, we can look at the composite function rule. As before, we let u and v be functions of x, and in this case, so that f of x is equal to u of v of x. Then, the composite function rule states that f dash of x is equal to u dash of v of x multiplied by v dash of x. Now that's quite complicated to say, let alone understand, so let's look at an example. Let f of x equal to sine of x squared. Here we have our composite function. X squared is an inner function and sine of whatever that result is as our outer function. So we let u of x equal to sine x and v of x is equal to x squared. Then, applying the rule, we end up with f dash of sine of x squared is equal to cosine of x squared multiplied by 2x, which gives us the result 2x multiplied by cos x squared. There is an alternative way of looking at the composite function rule. We can let y equals u of v, where v is another function such that v is equal to v of x. In other words, y is equal to u of v of x. Then the composite function rule can be written as dy by dx is equal to dy by dv multiplied by dv by dx. In other words, the differential of dy by dv multiplied by the differential of dv by dx. So if we have an example, y is equal to cos x plus x to the power 3, all raised to the power 4, we can let y equal v to the 4, and v itself be equal to the inner function there, cos x plus x to the power 3. So, dy by dv will be 4 times v to the power 3, and dv by dx will be equal to minus sine x plus 3x squared. The differential of the result, dy by dx, is equal to, according to the composite function rule, dy by dv multiplied by dv by dx, and that equals 4v to the power 3 multiplied by minus sine x plus 3x squared, and that gives us the final result of 4 times v, which is cos x plus x to the power 3, all raised to the power 3, multiply minus sine x plus 3x squared. Here are some more exercises for you to try. Please pause the recording here, and when you are ready to continue, please restart. And finally, here are the answers to exercise 4. That's the end of this lecture. Thank you very much for listening.